A random sample of 483 births gives the following two-way table. So here you are given the row variable age of mother and column variable birth. So the row variable can take three values. So age of mother can be less than 20, can be 20 to 29, 30 to 34, or 35 or older. And birth can be live or fatal loss. Okay. So the data shows that out of the 483 births, 49 involve mothers that are less than 20 years old and babies that are alive. And in this cell, there are 13 mothers who have fatal losses, and so on. I also calculated the marginal row totals and marginal column totals and the grand total. So here, the above question is fatal loss related to mother's age involve two categorical variables. One is age of mother, another one, birth status. The question is equivalent to asking whether the two variables are independent or not. So next, I'm gonna calculate the probability of observing mother that are younger than 20 and babies that are alive at the same time. Here, we are going to assume that the row variable and column variable are independent. If mother's age and birth status are independent, then the probability that mother's age less than 20 and birth status is live is equal to the probability that mother's age is less than 20 times the probability that birth status is live. So here we have used the definition of independence, which was introduced in chapter 4. Chapter 9. Okay. So if events A and B are independent, then the probability that A and B happen at the same time is equal to the probability of A times probability of B. So mother's age less than 20 with probability 62 over 483, because there are 483 mothers that were surveyed. Among them, 62 mothers are younger than 20. And the probability that birth status is equal to live can be calculated or can be estimated using this fraction. The denominator is the total number of mothers that were surveyed. And the numerator 387 is the number of live birth, or the number of mothers who had live babies. So if mother's age were independent of birth status, you would expect to see that 483, that is the total number of mothers, okay, and multiply by this. This is the probability that mother's age is less than 20 and birth is live. So that's the joint probability we just calculated here. Okay. So because the total number of mothers is 483, so we would expect this or this. Many mothers who are under 20 years old and have live babies. I hope this makes sense to you. And this number is called an expected frequency, or expected number, expected count, expected value, whatever you call. So that is expected if independence is correct. While the actual number, 49, in the original data is called an observed frequency. In this table, there are 8 observed frequencies, and they are denoted as O's. So actually, you can use 011, 012, 021, 022, 032, 031, 032, 041, 042 to denote the observed frequencies. The corresponding expected frequencies are calculated using the following formula: the row total times the column total divided by grand total, as demonstrated in the calculation of the first expected frequency. So another example for expected frequency is given here. So the actual observed frequency is 41 in the table, and the expected frequency is calculated as 242, which is the row total, times 96, which is the column total, divided by the grand total 483. So the expected frequency is 48.10. And expected frequencies are denoted as E's. So you can denote these expected frequencies as E11, E12, E21, E22, E31, E32, E41, E42. So E42 means the fourth row and second column. If mother's age is really independent of birth status, expected frequencies should all be approximately equal to observed frequencies. This is the fundamental basis for hypothesis testing we are going to introduce in the next slide. The general chi-square test of independence is outlined here. In step 1, you specify null hypothesis H0 and alternative hypothesis HA. H0 would take the form that the row variable and column variable are independent. An alternative hypothesis takes the form that the row and column variables are not independent. Step 2, calculate the value of the chi-square statistic, which is the sum of O minus E squared divided by E. So here O is an observed value, E is the corresponding expected value, and you have different pairs of observed and expected values. So if you have 10 pairs, you are going to have 10 terms in the summation. Step 3, calculate p-value. Keep in mind p-value is based on the chi-square distribution. And the chi-square distribution is almost always starts with the 0 point, and the degree of freedom is calculated using the number of rows of the table minus 1 multiplied by the number of columns of the original data table minus 1. So it's a simple formula. And step 4, draw conclusion. If the p-value is less than or equal to 0.05, then we reject the null hypothesis at level 0.05. Let's carry out the example. So step 1, H0 is that mother's age is independent of birth status, or there's no association between mother's age and the outcome of pregnancy. The alternative hypothesis is that mother's age is not independent of birth status, or mother's age is dependent, or birth status is dependent on mother's age. The second step, so we calculate the chi-square statistic value. Before we calculate that value, we have to find expected frequencies for all the cells. There are 8 expected frequencies to find, and the table gives the original observed values along with the expected frequencies in parentheses. So you should check all these expected frequencies are calculated correctly. So with the formula, we got chi-square value 5.89. So in the calculation, you should keep 3 decimal places so that your chi-square value is more accurate. And next step is to use a chi-square table to find a p-value. Keep in mind chi-square distribution is associated with the degree of freedom. So degree of freedom is the number of row minus 1 times the number of column minus 1. So it's 3. And based on the chi-square table, you can see that p-value should be greater than 0.1. And step 4, since the p-value is greater than 0.05, we don't reject H0, and we say that the test is non-significant. And we conclude that there's no association between mother's age and the outcome of pregnancy.